I'd like to welcome everybody to the webinar today on debugging multi-threaded C++ applications. You probably already know Greg, you've probably heard of him, but if you don't, Greg is a C++ debugging expert. He is a very seasoned conference speaker and the founder of Undo, which is the time travel debugging company for Linux. I'd also like to introduce Davit. Davit is a software engineer with AWS. He is an experienced engineer and works on the migration engine for AWS database migration service. His expertise includes large-scale debugging on multi-threaded C and C++ code bases. So, Davit, over to you.
Hi, everyone. I'm Davit. I'm a software development engineer at AWS DMS, which stands for Database Migration Service. And here at DMS, we know firsthand what it's like to debug multi-threaded applications at scale. And I have to say that the race conditions are one of the hardest and scariest issues to debug. So I'm here to talk about one of the examples from my time at DMS, one of the trickiest race conditions I've seen, and I had to solve. So let me get started by introducing a very high-level picture of what DMS does to get some context. So let's take an example of a customer who wants to migrate data between two databases. We call them source and target databases. And a very high-level description of what DMS does would be the following. First we connect to the source database, then we connect to the target database, and then we get data from source database and write it to target database. So it's pretty simple. The idea is pretty simple. Well, even higher level description would have been that we just read from source database and write to target database. But I mentioned connection for a reason, because that's where the issue was, and it would take away the ability for DMS to connect to the database. And we'll be focusing for the rest of the story with the connections. Okay, let's dive into the issue now. So the symptom of the issue was the following. So it was just, this is kind of a line from a log. And after running for some time, DMS was just unexpectedly unable to connect to a database. And it was logging that it was trying to connect at some gibberish address. And this was not deterministic. It would happen intermittently, pretty hard to catch. And it would happen once every 10 to 20 runs for a specific customer, or maybe after a couple of hours. So when I saw this gibberish address, it told me that there was a memory corruption happening, and I had to dig deeper on why was that specific memory getting corrupted and what was the specific memory at all. So when I checked out the code line, what I found is a C struct, which held some of the fields that were needed to connect to a database. For example, a DB address, which would just hold an address of where this database lives. And then I found out that this struct was shared between threads because multiple threads might need to connect to the same database, and it wouldn't make sense for each of them to fetch their own address. So we just have a shared struct, shared information between threads. And at this point, it was pretty clear to me that another thread was messing with the memory of the thread which was trying to connect. But since the logs didn't help, I had to try another thing we usually do, which is to reproduce the issue in our environment. We do that by trying to replicate the customer's environment and try to get the issue happen in our environment so that we can freely debug. I'm saying that because we cannot really debug in customer environment because we might get exposed to customer data and we take it pretty seriously to not do that. So we just try to have the issue happen on our environment without the data. And then we can use the tools, for example, that Greg will talk about in this webinar. So what I did was I tried to do the repro many times and recorded each run with undo. And because this is an intermittent issue, you don't want to be Like, for example, if you use GDB and you miss the debug point, you'd have to reproduce again. So I was trying to just get one recording. And after a bunch of runs, I was finally able to catch this issue with recording. And now that I had the recording, it should have been easy to debug. But even then, it was not as simple as I expected. And I had to heavily utilize memory watch points and the awesome last command in UDB to find out where this memory address was last modified to see where this gibberish came from. For those of you who are not aware what these watch points and the last command are, I included specifications on this slide, and I recommend checking them out. They're pretty useful. So to continue with the story, the first usage of last command took me to a place which is kind of a random place in the code. It was not very relevant. It was just zeroing out some memory. It was just overwriting the memory, let's say, and it was even if I stepped out of it, it wasn't saying, the call stack wouldn't say what happened or why the memory got corrupted. So I had to dig deeper into the program execution. So what I did was I went back to the start of the recording. And at the time, I was really thankful I had undo recording because I wouldn't have to reproduce it. And since I already knew the address that was being corrupted, and it would stay the same because it's a recording. So for every replay, it would stay the same. So I set up a memory watch point and just followed through the code execution, which threads were, how we're interacting with this address and the owners of this memory. And this is where undo really shined because you cannot really forward debug these things. Achieving the same thing with GDB would have probably taken me some light years. And with undo, I did it took me around 2 hours. Okay, now let me reveal what I found as a root cause. But to do that, I'll have to briefly explain what memory pools are, since they're very relevant to the root cause. So memory pools are a way to make memory allocations in C and C++, which makes managing memory easier and safer. So instead of doing malloc directly, you go to memory pool, which holds this pool of pre-allocated chunk of memory, and it just, when you ask it to give you memory, it just gives you that chunk of that amount of memory, and it also tracks the allocations. And one more big benefit of memory pool is when you destroy the pool, the whole memory is gone. And even if you had a leak in that pool. So it is also very tied to component life cycles. And if you make sure to destroy the pools as components are recycled, then even if you had a memory leak in the component, it will ensure that this memory leak doesn't propagate to the whole program. So for us at DMS, our components like threads can have their own memory pools. Let's remember this while I describe what the real culprit sequence of events was. Okay, let's go back to the AWS DMS and the structure, the credential structure. We also have a thread which wants to connect to a database. It has a memory pool. And to find out where this database lives, it must get this information somehow. Let's say it needs to ask somebody where this database lives. And that somebody would be this server at the top. Now, once the server tells to where the database lives, it needs to remember this information. So to remember a string in C or C++, you need to allocate it somewhere in the memory. And in this case, this would be this memory pool. So that means that the DB address is now pointing at the memory pool of thread 1, which contains this DB address. And for some time, this is okay to connect to the database, and everything is going fine. Thread 1 is connected to the database, and at some point, thread 2 appears too. And it also needs to talk to the database. So what it does, it goes and reads the address from the same credential struct. and then connects to the database. And everything is still fine. Some time passes, the threads do their work, and things go wrong when at some point, thread 1 dies. Maybe it just finished its work and it got cleaned up or something else happened, but it died, and memory pool was freed. So that's pretty big for all the threads that want to connect to the database, because thread 1 was holding the ownership on the memory where credentials were allocated. So if we look at how situation looks like now, it looks like this. We have this credential struct, which has this DB address, and it's still pointing to the correct string, but this piece of memory is now not owned by anyone. We have thread 2, which is happily connected to the database. Nothing is bothering it. It does its work. It can even reconnect if it wants to, because if it wants to reconnect, it goes to DB address, gets the correct string, and it can reconnect. But eventually, something bad will happen given enough time. And that something bad is overwriting the memory where the DB address was written. Because now it's not owned by anybody. Anybody can grab it, write whatever they want. But now what that means is the whole system, and for the whole system, nobody knows where this database is located anymore. So if some thread or existing thread, some new thread or existing thread wants to connect to the database, they cannot, because nobody knows the address. So that's why next time somebody tries to connect, we get this following error, that there's a gibberish address. Okay, so what's the lesson here? The lesson is that we should pay attention to component life cycles. If there's no clear relationship between component life cycles, it can cause some pretty bad race conditions like this one. And that's because a component with longer life cycle might end up depending on a component with a shorter life cycle. So what about the fix? There are multiple ways to fix it and remove this dependency. The fix can be as simple as just giving the longer living object its own pool, which has the same life cycle as the object. So from now on, the credentials will be allocated in this pool, and the dependencies of mismatched life cycles are decoupled. So yeah, this was it from my side. I hope you enjoyed it, and thank you for listening. And over to you, Greg.
Awesome. Thank you, Davit. Yeah, I just had one quick question on that, because when you talk about, you mentioned that this is working at scale, and every time I talk to somebody from AWS, the words at scale at AWS mean something different than I think than certainly that I'm used to. That some of these scales are huge. Do you have an idea roughly how long like when the bug happened, like that, basically that memory pool was cleaned up, and how long later until you kind of got the notification when there was that like cannot connect to gibberish? Do you have any idea of how long that span was?
Yeah, so that's not deterministic. It was different times, but the average, I would say 2 hours, as I had in one of the slides.
Wow, 2 hours. So that's that is a that's an eternity in computer time, isn't it? And yeah. Cool. All right. Thank you very much for that. I'm going to share my screen now and go through some. We're going to go a bunch of examples, fairly quick fire, and we're going to see a bunch of different tools and techniques that you can use to debug these pesky race conditions. So let me just. Awesome. All right. Yes. So I really urge you to play along at home. So you can clone this GitHub repo. It's got a couple of example files in it, and you can follow along the tools and techniques that I'm going to do, and you'll learn much better when you're actually doing it. So yeah, so clone that while we're talking, and then you'll be able to follow along, and you'll get much more value from this. Okay, so here's a quote that you may know. This quote is quite well known from a chap called Brian Kernighan. He's really grandfather of modern computer science, one of them anyway, and he He invented C and Unix, among other things. And he says, this is quite an old quote now, a few decades old. He said, everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? And I think that's quite, it's quite insightful, quite witty. Really, I think what Kernighan means here, his main point is keep it simple, right? You're not quite as clever as you think you are. But I think there's also an interesting corollary to this, which is debuggability. It becomes like the limiting factor in how good our software can be. We think of debugging as kind of like, I don't know, like the washing up or something, right? But it's actually completely core to software development. And whatever your metric for good is, how fast my code runs, how small it is, how quickly I can write it, whatever. If you make it twice, if you're twice as good at debugging it, you can make it twice as good. And when we're talking about debugging in general, I think what we're looking at is this how we had certain expectation and reality is diverged from our expectations. And the process of debugging, really what we mean most of the time when we say debugging is that root cause analysis, determining where did reality diverge from our expectations. Obviously, in practice, it can also be a bit like that. Or you can think of it as like you can think of this as an ultimate needle in a haystack challenge in a way, right? You've got, as Davit said in that case, running for hours sometimes, and you're trying to find that point of divergence. And what we're doing is we're just all the time, you're getting different clues, you're getting different pieces of the jigsaw puzzle, okay? And you build up this picture until you can see what actually happened. I think what makes bugs, I've said here, bugs hard to fix. Actually, what I mean is bugs hard to find, hard to root cause. Is really two things, right? It's how long is it between the bug itself and you noticing, okay, up to 2 hours in Davit's example, might be, even just a few seconds. That's a long time in computer time. The longer that is, the harder it is. By the way, this is why assertions are so useful, because what they do is narrow that window between the time of the bug happening and you noticing. And then the other kind of axis here is how deterministic are they? Does it fail in a different way each time? Is it every time I get that piece of a jigsaw puzzle, it's for a different jigsaw? And of course, life gets really challenging when we're up in the top right corner here, or even right, we get the Heisenbugs, okay, where every time we try and get a new clue, we get just the process of getting a new piece of the jigsaw puzzle changes the behavior, perhaps makes the bug go away. And race conditions tend to live in the top right of this corner. They're, by definition, they're non-deterministic, and they tend to have a long time. It's very common for them to have a long time between the bug and you noticing. And that's why race conditions are so hard. Let me just define very quickly what I mean by race condition. I think we probably all know, but just to really, I want to actually, well, not so much pin down, but actually broaden the definition. So I define a race condition like this: concurrent threads of execution acting on a shared resource such that the ordering of operations affects the outputs of the program. Bit of a mouthful. Let's take it piece by piece, right? So concurrent threads of execution. Now, that doesn't need to be a thread in the kind of operating system sense of the word thread, right? It's just concurrent execution. So it could be multiple processes. It could be the process and a single-threaded single process and the operating system. They are often concurrent threads of execution, acting on a shared resource. So again, the canonical example tends to be 2 threads, piece of data that's being shared, just like Davit's example. That's a very common example, but it doesn't have to be that. And often it's not that. The shared resource often is something like the file system. Such that the ordering of operations affects the output. So my 2 threads are in a race, and depending on which A and B, both operating on this shared resource, and whoever gets there first wins the race, and that affects the output. So a bunch of tools that I want to go through. This, of course, nothing like exhaustive, but we only have the hour, so I'm going to give you a taster of each one. They're all very useful. They all have their own places, and being great at programming necessitates you're great at debugging. Being great at debugging means you have to understand the tools that are available and know when to use which tool. Too many developers, in my opinion, just always rely on printf. I haven't said printf here. Printf is a useful tool. It has its place in the world, but so many people just rely on printf all the time, and they dismiss these tools as, oh, well, for whatever reason, couldn't reproduce, couldn't use it. And we're not looking for where won't these things work, right? We're looking for where will they work, and then you select the best tool for the job. So let's get started, okay, with some actual code. So I've got here, if you've cloned the GitHub repo, you'll have access to simplerace.cpp. Let me get my make that a little bit bigger. So Yeah. Okay. So what could be simpler? This is the very classic kind of, this is as small a race conditions I could make. It's been C++20. I've got 2 threads and they're both writing to this shared data, and then one or the other is going to be output. So you can do this at home. So it's bear in mind it's C++20, so you need that in order to compile. Let's get some debug info and let's compile it. And if I run it and do that, you can see that most of the time it returns 0, but sometimes a couple of points here it's returned non-zero, it's returned 1, because it's not going to be a mystery to know why that is, right? But this is just the simplest example I could come up with, and then we can run the tools in this example and see kind of what we get. So the question here, what are the possible return codes? Roughly what probability? 0 or 1? 10 times, 90% is 0 and 10% is 1 or something like that. It's actually, I've got a bit lucky, quotes lucky here. Usually when I run it, I see it more like 1 in 50 or something being non-zero, but whatever, some small probability of it being non-zero. So let's use the first tool today we're going to look at is Valgrind. It's a lot of people know Valgrind by the default tool. Valgrind actually is a suite of tools that will do kind of runtime dynamic program analysis. The default tool, if you don't specify this -- tool option, what you get is memcheck, which is the original kind of Valgrind tool. But since that was originally built, well, gosh, 15, 20 years ago, lots of tools have now been added to the framework, and Helgrind is a very useful. There's also DRD, data race detection. They're kind of similar things. And so if I run this now, and again, you should be able to do this at home. If you haven't got it, this is in almost all package managers. So, sudo apt install Valgrind or whatever tool. And by the way, I can tab to see the different tools that are available. And we're going to use Helgrind today. And then I just run my program as normal. Okay, so that's how it works. And yeah, straight away, let's make this screen a bit bigger so we get a bit more real estate. So here we are. Look, it's told me that there are some problems. These are just announcements, so you can not worry about these. But then here, look, possible data race during write of size 4 by thread 3. This conflicts with a previous write of size 4, thread 2. And indeed, that's what we're looking at. And it gives me a backtrace of what happened there. And of course, here we are, simple race.cpp, line 11 and 12. Which, if I go back to that, we can see that's line 11, and trust me, that's line 11 and that's line 12. Okay, I mean, obviously, I can just look at that code and see the race condition, but you can imagine if this was in millions of lines of code, that's really useful to tell me this. What's going on here is we're looking for multiple threads where they're all accessing the same piece of data without some kind of common lock held. And we have at least one of those accesses is a write. So yeah, so that's Helgrind. Very useful it is too. Let's have a look now at ThreadSanitizer. The sanitizers are kind of an equivalent to Valgrind really in the various tools, newer and much higher performance. The runtime overhead when you're running Helgrind, I mean, it depends on the program, but you can see everything from like 100x to 1000x. Sanitizers tend to be more like in the kind of 2x range, maybe a little bit greedier with memory, but so much more practical to use in many more scenarios. You still probably wouldn't use even the sanitizers like always on, right? The overhead's just too much for that, but you can use it in more stressful kind of situations. It's unlike Valgrind, which just runs on unmodified binaries. You see, I didn't do anything special there. I just compiled my program as normal. I did -G so I could get the backtrace line information, but I don't need to compile with -G. It'll work okay. It doesn't give you line information, but it'll still work. This is a compiler option, so I have to recompile my program. But by doing that, then that's kind of how the sanitizers work with that much more performance. So yeah, so I compile it just like before, except now I'm going to say -f sanitize equals thread. And now I don't run it inside any other tool. That's it. It's now a sort of self-contained checking. It's going to sanitize itself because, as I said, it is a compiler feature. So I can just run it as normal. And now I wanted to show you this. On modern distros, you can get this problem because it's basically to do with address space randomization. Don't panic. If you see that problem, we're just going to copy that and And very quickly, okay, those addresses are different, but here's the answer, right? So sudo sysctl to have fewer bits of address space randomization. The only thing is sometimes you don't have access to sudo, for whatever reason. So that in the case you do have sudo access, just do that. But in the case you don't, little trick, you can go setarch -r, and that will run without sudo access, without address space randomization. And so now it works. And yeah, here we are. So pretty similar to before. It's a little bit, the output's a little bit tidier, a little bit easier to read, I think. But basically the same. It does its threads announcements down at the bottom because that's probably not as interesting. I think that makes sense. And bit of color, bit of color here so I can see, yeah, possible. So data race. It's a bit more assertive rather than possible data race. It says it is a data race, and I'll get into what it means by that in a moment. We got it again right, conflicting with the previous write size for these addresses, and here the backtrace is just like before. So pretty similar, maybe a little bit richer output from the sanitizers, and runs a lot faster. And again, like I say, you just choose the right tool for the job. And I think for the most part, I would say if you have the ability to recompile your code these days, most people will probably go for the sanitizers just because of the performance. But you may not. You might work in a big company and somebody else owns the build, and you can say, can you dash f sanitize to my program, and they'll maybe that comes back in a few weeks with them having done it, maybe not. Maybe you don't have access to the source code and you suspect somebody else is. I've been in that situation myself. So there are still perfectly valid times when Valgrind comes into its own. Actually, they also just will find, just the nature of these things, they will find slightly different things because the program is going to run a slightly different way. Timings will be affected and things. So that Heisenberg principle. And it's actually I'm reminded of, that you probably remember the XZ attack from a couple of years ago. Very, very sophisticated attack, or XZ. It was caught in the end by somebody from Microsoft. Noticed a weird half-second delay when they SSH'd onto a box, and they found it. It was almost caught before that by the people at Red Hat when it failed some Valgrind checks internally. All the other checks passed, but Valgrind was throwing some errors. And it just happened that one of the maintainers, who was actually one of the bad guys, fixed it, and jolly good, off they went and released it. And it was the smoking gun was actually there, but they ignored it. So I think that's another lesson here, is that when you get these failures from Valgrind, Sanitizer, or whatever, it's tempting often to say, oh, it's giving me a false positive, and you know what, most of the time actually it's not, and it's really worth fully understanding when you get the warnings. So yeah, let's get back to the slides. So that's Sanitize, ThreadSanitizer, and Valgrind. There's lots more. I'm just giving you a tiny taster. There's lots more to them about the different options and what you can track and everything. But that's kind of in the nutshell how they work. They are, by the way, I think very easy to use. And sometimes people kind of back away from them because it's kind of intimidating, because they feel like they're kind of magic, and they are kind of magic, and so therefore they must be hard to use. And they're not. These tools are. Have you just seen how easy it is to use? Okay, a little bit finicky with the address space randomization there with ThreadSanitizer, but quick Google and we had the answer. Okay, so usually people, or the sort of default answer of how to fix race conditions is to use mutex or some kind of lock, some kind of protection, right? So let's change our program, as I've said here in the slide, yeah, what do we think on the chat? Can we have some answers here on the chat? Does this fix my race condition? I'll wait. Let's see. Anybody gonna volunteer an answer? Oh, well, while we wait for somebody to answer, do answer. It'd be good to know that someone's out there. I've actually got should fix, but the result is non-deterministic. Exactly. I mean, it's kind of a nasty question because it depends what I mean by the race condition. Now, if you remember my definition of race condition, no, it doesn't fix the race condition. It does. It turns it into valid C++, and I'll get to that in just a minute. But yeah, of my so if I make the change and it looks like this, there's my mutex. So let's try that. G++, let's do, let's compile it. So the second question was, what does Sanitizer and Valgrind think? Oh, yeah, of course. Well, so no warnings from Sanitizer. So ThreadSanitizer thinks that's fine. Let's try it in Valgrind. So I need to compile that normally, and no errors. So yeah, by my definition of the race condition, that this does not fix the race, right? Absolutely does not fix the race, because this assignment, what the mutex does is like make it deterministic, make it atomic, right? And this assignment to ret is already atomic, so I'm just making an already atomic thing be atomic. There is no guarantee about what order this will run in, and so therefore the results of my program will be affected by that race. Okay, so by my definition of race condition, this absolutely does not fix it, but it does make the errors go away from Valgrind and ThreadSanitizer because of the way those tools work, right? They're looking for, as I said earlier, they're looking for concurrent accesses to a piece of memory with a common set of locks held. And I now have that. I'm doing that, and so those things are happy, right? So the point of this is really two things. One, mutex is not always the answer, and two, just because you get a clean bill of health from ThreadSanitizer or Valgrind does not mean that you are race free or anything like it. Okay, it's a if you get it's more like if you do not get the clean bill of health, then you probably do want to look at it. Yeah, so, and I think this is one of the things that I find most commonly, in my opinion, is it's sort of most misunderstood about race conditions, or misrepresented, that we always have this kind of canonical version, just like the simple race that I just showed you, right? That's the classic canonical version of a race condition. If you look race condition on like Wikipedia or CS 101, or maybe it's CS 201, I don't know, but it's the canonical version. But it's like, I think about 10% or something of races, a minority of races are actually due to concurrent OS level threads accessing some kind of shared data. Much more common to race with another process, to race with the user, to race with the OS. I'll just give you an example. We had one a little while ago in Undo, where our test system, when it finished running all the tests, it would clear up the temporary directories. And so it would just go, there'd be a little check. It was a bit of Python code, very simple. If the directory exists, then remove it. And this worked fine until one day, two versions of the two copies of the test were running in parallel on the same machine, and they both did that check and use at the same time. So both went, does the directory exist? Yes. Yes. Okay, fine. Delete it. And then whoever got there first managed to delete it, and whoever lost the race got an exception because it now doesn't exist. So that's a classic. What I'm talking about is classic, what we call the time of check, time of use race. That's two processes, both single threaded, and the shared resource is the file system. So I think, yeah, that's I think. And of course, ThreadSanitizer and Helgrind won't help you with those different kinds of race, which actually I think are probably the majority. So yeah, the canonical race X never marks the spot except when it does. Okay, let's get in quickly. I want to get into the C++ and C from C11 and C++11. They both have this. They introduce this kind of formal memory model which talks about this stuff. So prior to that time, there was no notion of race conditions and races in C or C++. They've now kind of defined that. And if you want to know, I'm not going to get into the details of it. We don't have time today. In fact, I find with many of these things, let's just ask. Please describe the C++11 memory model as applies to race conditions. And here we get so obviously you're going to get this differently every time you run it. Maybe this was the one I did this last time when I was practicing. And it gives a nice overview, right? And the key thing with the C++ memory model is this notion of the happens before relationship. Okay, so we say something happens before A happens before B. If all of A completely takes effect before B takes effect. And this matters, particularly with modern CPUs, modern multi-core CPUs. You can get this out of ordering, these out of ordering effects. It can be very confusing. If you have mutexes and locks in the right place and atomics, then this goes away. So what this means is, it's a whole hour's talk just about this stuff, to be honest. But what this means is this change to add these mutexes here, that has at least made this valid C++. Prior to this, without those mutexes, it's actually undefined behavior. So previously, I had not just a race condition, I had undefined behavior. And so it could return 1, it could return 0, it could return 2 if it wanted, it could return 42, it could rm minus rf my entire file system. Like, it's literally allowed to do anything it wants without those mutexes. It is undefined. And so that's really when, Sanitizer in particular is really looking for that, what's defined in the language. In the theory of Valgrind is a little bit different. It's more looking at like bits and bytes underneath, because it doesn't happen at the language level. Your code doesn't need to be even written in C or C++ to use Valgrind. It could be assembly. You can run Valgrind with assembly code, right? It's like the same at the conceptual level, but when you get really into the nuts and bolts of like what is it looking for, what's it saying about your code, that's kind of a big difference. In practice, in practice, without if I go back to the original one, this, like I say, it is allowed to do anything. In practice, it is going to return 1 or 0. Okay, and as we saw when we ran it, just be aware of kind of that, and you kind of need to understand that memory model, particularly when you're running on modern multi-core machines, where you can have these sort of weird effects where one CPU can write incrementing value 0, 1, 2, 3, 4 to the same piece of memory. Another CPU might be reading that same piece of memory, and it won't necessarily read those in the same order in which you've written. It might read 1, 3, 2, 4, for example. Okay, and it does that for so that otherwise these things multi-core would run far too slowly with cache synchronization and the like. Right, we need to keep moving on. So, and Davit talked about this earlier on, and I think this is obviously this is a matter that's close to my heart, something I've been working on for many years now. But time travel, I think, is very useful because it's not looking for the occurrence of certain bad things in the way that sanitizers and Valgrind are. It's just showing you what happened, and it's up to you now as the programmer to decide whether this was a good thing or not. So I've got here, so I've got my program. If I run it, so it normally returns 0. So I can run it in a loop like that. And you can see, it runs a bunch of times, but eventually it's returned non-zero. We can, just for completeness, do it like that. Anyway, oh yeah, no, sorry, don't ignore me there. Anyway, so run it in a loop, and then until it returns non-zero. That ran for a little while. I'm going to run this inside live recorder, and I'm going to run it with thread fuzzing. And what we're going to see is this is just going to run a bunch of times until it stops. And so it's run a few times, then it stopped, and it saved the recording here. Now this recording is it's a bit like a core file, except it has the full programs. The core file has a program state just for the kind of at the very end for one moment in time. The recording has the full program state for every single instruction that executed. So it is like having a core file for every single instruction all joined up together. I'm going to load that up into UDB, and I'm going to put a breakpoint on main and continue to that point. So what I'm doing here, I'm not stepping through the program live, I'm stepping through a recording of what happened. So one single recording. So although the program is non-deterministic, I've got one execution of that. Let's go into TUI mode so we can kind of see what happens. So let's put a break on 18, because that's the line 18 where it quits, and continue to there. So now if I print ret, we'll see, it's 1, it's non-zero. That's kind of what I expected. So I want to know when that changed, and this is what Davit was referring to. So I can put a hardware watch point on that, and now I can reverse continue to go back in time to when ret was most recently updated. Okay, so there we can see it's being set to 1. I can go back again and there it's being set from, it was set from 42 to 0. So I'm going backwards. So it was 0, now it's 42. And I can go back again. And this is where it's kind of originally set. So it was previously -1. And I can go, that was going, and I can go forward. Maybe it's a little bit easier to see what's going on when we go forward. So continue. Okay, it's set originally to 42 at the top there. Continue again. Okay, this thread T1 has got there first. I run it again. And the point is, every time I run through this, it's going to have exactly the same ordering of operations, exactly the same sequence. You know, obviously, you know, a few lines of code here, but this can work with at very large scale with millions of lines of code, and you can see how, hopefully you can see how that can be just incredibly useful, because I just have to capture one run of the program and I can investigate that to my heart's content, and I can follow the control flow and the data flow through. So that is time travel, which I think is pretty awesome. I just want to say a note, actually, a little bit of a tangent, but this is really important. Very often I see that people synchronize by sleeping, and it's always a really bad idea, right? Because whatever value you choose, unless you choose to sleep for like an hour, then your program just runs unusably slow. You choose, oh, I'll go to sleep for a second, and whatever value you sleep for, eventually it won't be enough, right? Something will happen, the system's thrashing, you're running in the cloud and it gets migrated, and VM gets migrated from one machine to another or something like that. So I can add this sleep. But one thing I like is, I'm going to go back to the sanitizers now. Valgrind doesn't do this, by the way, but simple race. But if I put this through, I thought this was neat. So if I run that program in practice, it's very difficult to get it to return anything other than 0, but eventually it will. If I run that with the sanitizer, sanitize. By the way, I can do tab and see all the different sanitizers, but we're looking for ThreadSanitizer, simple race sleep, and now, oh, sorry, standard equals cplusplus20, and now I run that. Set up. I like this. It says as if synchronized by sleep. So it's figured it out. It's figured out I've got some sleep here, and that's a nice kind of pointer that this is probably bad and bad news. So yeah, sleep is just a big red flag. Like sometimes a sleep is legit, but in my experience, most of the time, it's a race condition waiting to bite you. Let's look at AI. Obviously, that's, you know, can be very, very helpful, perhaps looking at the code statically. So let's run this in Claude code. Yeah, let's say, right, so we'll say, is there a race condition in simple race.cpp? Now, I would fully expect Claude to get this right. It's the absolute canonical example. Even the program's called simple race.cpp, so that's going to be a big clue to it. Sounds a little thinking, but yes, there we are. There's a race condition. So good. If I had millions of lines of code, I think that's a much harder job for Claude. Or any LLM, just, you know, it doesn't fit in the context window. And generally, it's not just the context window problem; it's also the kind of bug density, right? So this example here, very, very high bug density. I've got like 20 lines of code, and the bug is on like 2 of the lines. But you know, if I've got millions of lines of code and the bug's on 2 of the lines, it's a much harder job for the LLM to find it. What you can do though is combine. You know, LLMs can now use tools. So we can, and that's where things start to get really cool. So we can combine, by the way, you can combine time travel with the sanitizers. You can also combine time travel with the AI. So let me load that up again. This takes a little bit longer, so I'm going to just kick it off and then I'll go back to the slides. So that's the thing I was just looking at. Let's delete all the breakpoints and everything. Yeah, let's be harsh. And I'll this is experimental, so I just need to fetch the explain extension, and that will just download in just a second. There we go. And so now I can say explain, why did this run of the program return 1 rather than 0 as I had expected it to? And now it's going to go away and not look just at the source code of the program, but it's going to look at that execution, and it's going to look at what really happened in the program. And so combining it like this is kind of, I think of it sometimes as like an antidote to hallucination, because we're kind of boxing in the LLM here to like what lines of code actually ran, what was the data. In some ways, you could say it makes a bit of a meal of this. I just showed how easy it is to do this, for it to do it statically. This is a tiny program, but yeah, again, much bigger programs, this really comes in to its own, and it's kind of squeezing down the context to what really happened and what's important. So it's going to traverse through a bit like I did when I ran the demo, and I'm going to leave that going because it takes a little while, and yeah, it's AI, so sometimes it does something a bit unexpected, but we'll see how that gets on. Lastly, I want to talk about using GDB. I hear people, I just hear from time to time, people say GDB is not good at debugging threaded code and debugging race conditions. And I don't really know why. Well, I have a couple of theories. I think one is just sort of historical and no longer true. So if you were saying this 10, well, maybe say 20 years ago, then yeah, you probably had a point. Threads on Linux was kind of in its infancy. Everything was kind of a little bit broken, and GDB was pretty buggy, and generally the experience was not good. That has like not been the case for a long, long time, at least a decade. It's basically I would say it's pretty damn solid. I think the other reason might be that people kind of misunderstand how it's supposed to work and what's available, and particularly around like scheduler locking. So let me quickly show you this. Let's see how we'll leave Claude to get on. I think it's getting pretty close there. We'll leave Claude to explore that. So yeah, I've got a different program here, threads.c. So let's compile that. And when I run it, basically what it's doing is it's got 4 threads, and they're all updating an item in spinners. This is actually undefined behavior because of the way they access the spinners array, but in practice it works. So let's just have a look at that quickly. So I've got these 4 threads. They all run through this looper function, and it just runs around this loop, and it's just updating. Each thread has its own index, and it's updating that thing and printing it out. And so let's run it in GDB. Okay. So when I run it, oh, by the way, another thing that's I think misunderstood often is that this program is now running at full speed, even though it's inside GDB. Because there are no signals happening and there's no shared libraries happening, then shared libraries are being loaded and unloaded as it runs. Then it's just GDB's out the way and it's running full speed. But when it hits a breakpoint or gets a signal, then obviously things happen. So Control C gets a signal, info threads, and actually sorry about that. Do you know what I've done? I've accidentally run that in. Let me do it in proper GDB. Run that. Ignore that. Right. So there we go. So it's running away. Control C. So info threads. So I've got my 5 threads, the main thread, and the 4 worker threads. And what I'm going to do is this looper. I'm going to put a breakpoint on line 17 and continue. Okay. So I'm going to go into layout source, and I am going to let's display the spinners array so we can see this as I step through it. And I'm going to do so. Yeah. So which thread am I in? I'm in thread number 4. And so which is like the penultimate worker thread. And so as I do next, I'm going to just sorry, let's get rid of that breakpoint. Right. So I'm now in thread 2. So as I do next, we run it's thread 2. So we can see what's happening as I do next. So this one, I was actually right at the end, and it looped round to A as I did this. Of course, is in this if. But look, so this isn't moving now because I'm not in these incrementing spinners or anything. But look at the others. This has gone. It's got S to G to J, D to T to S, P to N to X. So the other threads have made quite a lot of progress, and that's by design. And it can be confusing. I'm always going to stay inside thread number 2 unless something else happens, unless I get an external signal or I hit a breakpoint or something, and then it'll switch to that other thread. If I don't want that behavior, by the way, I can just set scheduler locking on. And now when I do next, it won't run the other threads. It'll just move the thread I've got forward. So let's watch that. Okay, that's so you can see the other threads aren't running. The reason that's not the default though, if I set scheduler, let's switch to a different thread. Let's switch to thread. Actually, no, let's info threads. So I'm in thread 2. They're all kind of in a nice place. If I set scheduler locking, I actually got a bit lucky there. That doesn't usually, or unlucky, that doesn't usually happen. So let's set scheduler locking off. Let's run it a bit. And now info threads. And I can see most of them in this mutex wait, and one is in right. So if I now go thread 3, set scheduler locking on, it's inside the C library. So let's finish out a few lines until we get to what we want to get to, and it's got stuck, right? And this is the problem, because most of my threads are waiting in this mutex, and thread 5 is in libc right, and in the middle of libc there's this kind of big giant lock, and so only thread 5 can make progress. So thread 3, and in fact thread 2 and thread 4 are all waiting for the lock. Thread 5 holds the lock. I set scheduler locking on, so when I do next on thread 2, 3, or 4, thread 5 isn't moving, and so it's never going to release the lock, and those threads are never going to run, and that's kind of even more confusing. And so that's why GDB has the default that it does. You can play around with this. There are other options for scheduler locking, but that's kind of the notion. And I think that is sort of slightly misunderstood. And when you kind of understand that that's how things work, it all makes a lot more sense. The other reason why people sometimes say, by the way, GDB is not good for debugging race conditions, is because if I've got like timing sensitive things and things are timing out, like I've hit a breakpoint, I stop things, and like the other end times out or something. I don't think that's about race conditions and threaded code per se. I think it's, yeah, a stopping debugger is not good if you've got kind of time sensitive, real time requirements. You can take a recording, like I showed you with time travel. That's often a good way through that. You can also run GDB in non-stop mode. You can't turn non-stop mode off and on, but you can start up in non-stop mode, which lets the program kind of make progress as you're stopped at the command line, which is also kind of which can work there. So yes, again, it's just understanding what's available, what are the tools, different kind of strengths and weaknesses, and where should I use different tools. So yeah, let's go back now. Let's see how did Claude get on. Look at that, perfect. So I can see here it's gone through the code. It's analyzed what's happening. It's set watch points and break points, and it's moved back. It's actually set. Well, I'll show you this in a minute. This is quite nice. And it's given me a nice explanation here. See why your program returned 1 instead of 0. Program has a race condition between these two threads. Blah 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 blah. We know all that. But obviously, if that's a nice description of exactly what's going on, very carefully. If I look at the bookmarks, I can see it's set some useful bookmarks. It's set T0 sets ret to 1, main returns 1. So it's set it's a little bit better, see a little bit more easily here. So it's set some nice bookmarks in my program execution, so I can jump around. Okay, so if I want to go, you go bookmark T0 sets 1, we can go there and we can see what the program is doing, like at that moment in execution, which is quite nice. So yeah, there's a nice, as I say, sort of I think of it as a hallucination antidote. Inside GDB, I think you can it's a really useful thing if you're debugging. However you're debugging actually multi-threaded code, is to set thread names, and that just makes things a lot easier. So if I go back to this one, and these okay, I've got an older version of it. It doesn't set the names. That's annoying. You can set the names with piece threads. So there's a function called piece thread set name NP. The NP is stands for non-portable. And then if I set the name, I've got an older version of my threads program here. But if I set the name, then I would actually, and I see the thread name in here. And if I have many threads, being able to see the kind of name for them is useful inside the debugger. You can also see it when you're looking on proc file system and stuff. So yeah, give your threads a name. I think that's just generally useful bit of advice. I think that will do for what I wanted to cover. I want to have a quick look over to the chat, because I see some questions here. So let me just bring that up here. Yes, I think we will be providing a recording of the session. How do I install Claude code on my Linux box? Somebody's asked. It's pretty straightforward. I can't remember now. It was so straightforward, I can't remember how I did it. You will need the right kind of level of service with Claude. I think it doesn't work for free, but it's not, it's relatively cheap, and I really thoroughly recommend it. I hear people say also Codex is very good as well. AMP from SourceGraph, there are several of them now, but yeah, Claude was kind of the first one with that kind of really nice, I think, CLI. Where it nicely gets out your way, and you can just use it from within the terminal, which I liked. Oh yeah, here we go. So Magnus has already answered the question of how to install Claude. How about core dump debugging in GDB? Yes, that's a good point. So core dumps, core dumps are much, as I said, core dumps are really very like recordings, except they just give you like one point in time. But yeah, often, we've got a kind of production system. We can't afford to be, taking recordings and things, because that does definitely impose some slowdown. And, all we have is a core file to look at. Mostly that just works, I find. You might, if your program is stripped, it doesn't have the debug info in it, you might need to point GDB at the debug info, which you can do with the file command or the set symbol file command. So that's often a slightly tricky thing, actually, is pairing up the debug info and the source code. There's a really nice thing called debug info D. If you run that will help you. Inside, there's always a build ID when you just run GCC or Clang. It will always give you a build ID inside your object, and then that's a unique ID that you can then refer back to the debug info and the source code for that build ID. So yeah, do check out debug info D. Do you have a specific, so when all symbols are available for a crash dump and all of them are loaded and GG doesn't show a call stack, how can we troubleshoot the issue? Right, yeah, well, that's one of my favorite. This is almost like a plant question. So it's the case you've got all the symbols available and they're all loaded and it's definitely the right symbols and everything, and you can't show the call stack. What it means is your stack is corrupted. And that typically I've written into my stack and then returned off the stack, and I've returned into hyperspace. That's a really nice case, by the way, where recording comes into its own, because we don't need the stack available to see what's happened. So the closest that most debuggers give you to what happened, which actually I think is always the question when you're debugging, right? It's what happened, past tense. And the closest that most debuggers will give you is looking at the backtrace, which is very useful. But only gives you a sliver of what happened. Of course, doesn't tell you anything about the data, doesn't tell you about any, only the function calls that are like directly in the call stack. And yes, if the problem is you've corrupted the stack, then yeah, you're in trouble. Yes, Rust, it works on Rust. So I think I might just have no, I don't. But I tell you where I do have it. Hang on a second. Undo releases, latest. So let's there we go, that's where it is. So here's one deliberately. This is really unsophisticated and uncomplicated, but deliberately crashes the stack. So if I go make and we run in UDB, we run. So if we run this so this is what typically you'll see, right? If you're looking in just a regular debugger, the backtrace is garbage because it smashed the stack. With the time travel debugger, we can just reverse step I, go back one single instruction, and now we've gone back to where the stack actually contains good data. So yeah, that's thank you for asking that question. What else do we have? We are kind of we're just over time, actually. So I see all the questions in the chat. I think mostly being answered. How big are undo recordings? Yeah, well, it totally depends on how big your program is run. My rough rule of thumb is a small number of megabytes per second of recording. It will change. It will vary, but that's kind of what you're talking about. So it's actually a lot less than you might think. And due to the way that it works, we're not recording every single line, every single instruction that executes or piece of data that moves around. That'd be far too heavyweight. So yeah, it's very efficient. Cool. All right. I apologize for going slightly over time, but there was a lot to get through and there's a lot of good questions. But thank you very much, everybody, for staying over and for the kind words. And yeah, that's it from me. I don't know, Sharon, do you want to say some closing remarks?
Yeah, I just wanted to say thank you to everyone for attending, and Davit, thank you. We were absolutely delighted that you could join today and share the content with us so well and articulating all your stories. So we really appreciate your time. Thank you. And Greg, thank you for your time as well. We will be sharing the recording at some point soon, so keep an eye out for that. And if you have got any questions unanswered, then we will come back to you directly. But thank you very much for attending, everybody, and we hope to see you at one of our other webinars soon.